Hi, I'm Jose, and I'll present the organizers solution for this task. We deployed a model where we approach the video using Fisher vectors, which is a method based on dense trajectories, and the acceleration part using a CNN. So these two are fairly different approaches. The reason why we chose to go with dense trajectories plus Fisher vectors for the video part is that our preliminary experiments showed that these are very this is a very competitive method when compared with last year's solution, which was based on multiple instance learning. I'll explain what this is a little bit later. And we also found that it was robust against one of the challenges that we have in the data, which is that people appear in very different orientations depending on where they are in the scene, because what we have is an overhead camera. And it's also a fairly simple method. There's a lot in action recognition using CNNs, but we decided to start approaching this problem, which is fairly new, with the most simple method that there is, that is also fairly competitive there in terms of performance. For acceleration, we found that logistic regression based on expert features, which is what we did before, was fairly strong, in the sense that it was a baseline that was hard to beat for this task. So we thought that the next step would be to use CNNs that are able to extract their own features and see how that performed. Then there's also the fact that they can take a larger context, so we're not limited to giving them, let's say, the 1 second windows, but we can also give them a larger context and predict for the 1 second window in the center. And also my preliminary experiments showed that they were competitive against recurrent models, so LSTMs. So for dense trajectories are extracted from a video basically by first extracting interest points for every frame of the video, and then you track those interest points along the video using optical flow. And then you describe basically the volume around the trajectory here using histograms of gradients, histograms of optical flow, and motion boundary histograms. So you are you're basically describing it using both the spatial information around the trajectory of that interest point, which could be, for example, a joint, or it could be in principle anything, and also motion information. So trajectories are normally about 400 dimensional, and they contain basically a very complete description of the volume around the trajectory. Feature vectors are basically a way of summarizing all these trajectories into a single high-dimensional vector. What happens is, in a particular window, you from a particular window you can obtain several thousand trajectories. The number of trajectories that you obtain is not fixed, because this is a sampling process, and you want to be able to summarize them into a single feature vector for classification. So that is what feature vectors allows you to do, and it is also used for other kinds of features like SIFT features and SURF features and image classification. But it is very common also in action recognition. And what you do is, you start with the windows or with the video. You extract the trajectories from the video. You separate them so you separate them in windows. In our case, we have 1 second windows. Then you sample trajectories from the original video, and then you learn a Gaussian mixture model on those. So you basically learn a generative model from those. It can be any generative model, but normally you choose a GMM because it's simple. And then what feature vectors does is you take one of those windows, which in this case is X here, and then for each parameter in the GMM, you obtain basically the gradient of the log likelihood of the model with respect to that. In case of a GMM, those are several thousand parameters, and you have one element of your feature vector for each parameter. So, for example, that results in 2k times d. That is where k is the dimensionality, and d is the dimensionality of. So in our case, this is 51 vector. It's very high dimension.